smart homes, manufacturing, smart buildings, doorbells, smart cities, light bulbs, locks, sensors for temperature, security cameras, connected doors, water and gas usage meters. The list just continues. Hundreds of devices, thousands of devices, millions of devices. The scale is unlimited. IoT systems come in all shapes and forms, and our architecture must be able to meet the demand in scale and cost. Today, we'll take a look at one of several cloud architectures I've been building out for IoT systems over the years with several different clients, the challenges we faced, and what we did to go event-driven. So in today's talk, we will do an introduction to AWS IoT. We'll look into a sample cloud architecture. We will look at our journey from IoT core to event-rich in an event-driven system. And we will round everything up with some takeaways and thoughts on our journey. But before we begin, who am I? My name is Jimmy. I'm the father of 2 girls, which makes me afraid of nothing. I'm a serverless, IoT, and event-driven architecture enthusiast. I've actually been working with serverless and primarily Lambdas then from 2016, early 2016. When I started out building architectures with Lambdas, it was actually one gig memory was max. There was no environment variables. That is how Lambda old I am. I'm an AWS ambassador and AWS community builder. And that's my night job. So in my daytime job, I work as head of AWS technologies at Sigma Technology Cloud, an advanced service partner with AWS. IoT, Internet of Things, IoT, Industrial Internet of Things, also known as Industry 4.0. What is it? What's the thing? How do we connect them? What is the purpose with all of those things? Hopefully I can answer some of those questions here today. The concept of IoT, it's a network of physical and virtual devices that's connected. It's a collection of data from several of these connected devices. It comes in with a wide range of use cases, as you heard in the beginning. It's rapidly growing. We are connecting more and more devices to the cloud every single day. And IoT, Industry 4.0, is an enabler for all the manufacturing companies to improve their manufacturing processes, their delivery chains, and how they build and operate in large-scale factories. Throughout the talk, I'm going to use this scenario for my architecture. We are talking about an architecture that could handle thousands to millions of devices. It will have an unpredictable traffic with a varying load. We're talking about high-speed, real-time data, and we are talking about asynchronous data processing. AWS IoT. So with that in mind, there are so many different components in AWS IoT. Today we will focus on some of the components in AWS IoT Core. Then on the other services you have within AWS IoT, you have Greengrass, you can bundle onto your devices for easy access. You have Device Defender for your security measures. You have your fleet provisioning system, fleet-wise. There are a vast amount of IoT services in AWS. We don't really have the time to go over all of them. That would be a 2-hour talk, I think. So let's focus on AWS IoT Core. What is it? It's a managed service to easily connect, register, and manage your devices. Comes with robust built-in security, authentication, encryption, and access control. It scales to millions and millions of devices, making it ideal for a huge IoT systems. It supports the standard protocol MQTT and HTTP. And it actually comes with an event-based architecture. X509 certificates, that's what we use in IoT Core for authentication of our devices. We are using mutual certificate-based authentication, meaning that the device and the broker each communicate and proves their identities to each other. We bundle a unique certificate per device. That's the best practice. I have seen other things happen. It uses a policy-based authorization mechanism based on the identities established by these certificates. IoT Core comes with a built-in certificate authority, meaning that you can provision your certificate needed for your devices from IoT Core if you need so. But it also comes with a custom support for custom CA, so you can bring your own certificate authority into the cloud. What is MQTT broker? What is topics? We're going to talk a lot about that today, so let's get that out of the way. MQTT broker is the server, the central service that all devices connect to, that sends all the messages and routes messages to different processing units. IoT Core comes with a very powerful rules engine for doing this routing. And topics are hierarchical, meaning that in this example here, we have 3 hierarchies. So we start with sensors, then we have the sensor ID and the temperature. And then we can build out our different topics based on this. So you could actually include IDs, temperature, humidity, and so on. IoT Core uses these topics as the way to route your messages to different services. What is an IoT thing then? We're going to talk about things. What is this thing? I've been saying this several times already. It's a representation of a physical or virtual device. And in IoT Core, it can be assigned to a thing type. You can create a type like a light bulb, dock, smart camera, and so on. And you attach your things to these thing types to easily group and identify them. Your things is what's published and subscribes for messages to your MQTT broker over these topics. Before we can start using our things in IoT Core, we need to register them. Then IoT Core need to be aware. What is your thing? Who is it? What's the identity of this thing? So what we do normally is you bundle your device certificate, your identity, onto the device during your manufacturing process. Then you can use just-in-time provisioning to provision your things in IoT Core. The reason for using just-in-time provisioning, meaning that you can have a lot of manufactured devices that has not been provisioned or registered, meaning that they can't access anything until they're connected. So how you do that is you attach a provisioning template to your certificate authority. So every time a thing connects to the cloud, this template will be run. Here we can use pre-provisioning hooks to do extra validation to ensure that the thing that is connected is actually the thing that we expect it to be. So if we look a bit on the flow, we have our thing connects to IoT Core. Our pre-provisioning Lambda hook is then run. It's been invoked by IoT Core. We can do then validation of the certificate and the identity coming from the device. We then return to IoT Core OK or not OK to keep provisioning. If we have an OK, we will provision a policy, a certificate, and a thing. After that, we will connect the policy onto the certificate, and the certificate be connected to the thing. And finally, we will enable the certificate so the devices can connect to the cloud. What is an IoT policy? It's a definition of permissions for the device to be able to connect. We attach it to either the thing directly, we can attach it to thing types, or with other IoT resources in the cloud. And it comes with a very powerful variable substitution for things and certificates. So you can use information coming from either the identity certificate or from the thing, like the thing name and things like that. Short example of a simple policy. In this one, we create an allow statement for a device to do called IoT publish, but it is only allowed to publish on a specific topic. So it's only allowed to publish to the topic with its thing name. That way we can limit what topics a device can publish to, what topic a device can subscribe to. So that way other devices can't listen in on data coming to targeted for a certain device. IoT also has an IAM credentials endpoint that operates over HTTP. What it does is actually you exchange of X509 certificate for temporary IAM credentials, and that you can use then to directly call AWS services from your IoT device. It could be that you want to upload something to S3 directly. It could be that you want to connect to a Kinesis video stream, to do WebRTC or similar things. This is very similar to the AWS IAM roles anywhere, but this feature has been around way longer than the IAM roles anywhere. So when we are sending data, the devices send data on topics, as I said. We organize our topics in a very good and structured way. In this example here, we say ingress, thing name, data. So devices connect to the topic, publish the messages. Then IoT Core uses topic-based routing to send messages to different services. When receiving data, we're basically doing the opposite way. Our services in the cloud publish messages to IoT Core on certain topics, for example, egress, thing name, data. And we have our devices have been subscribing to these topics and therefore receiving the message. With this powerful actually publish and subscribe mechanisms, we can actually build ourselves an MQTT-based API. So our things publish a message onto a topic. It could be an API action saying, instead of, in my previous example, getting temporary credentials from IoT Core directly using the IAM credential endpoint to get access to S3, we can instead call, okay, I want to upload a vast amount of data to S3, send that as an API action to IoT Core. We can then run our logic, step function, lambda functions, etc. And then we can return things back to the device. So in this case, we could actually return a pre-signed URL to S3 that the device can upload data to. So some brief and quick overview of AWS IoT and what IoT thinks. Let's jump into building out the cloud architecture and all the iterations we've been doing over and over again for these architectures. Starts fairly simple, like this. We had our things, all of them connected to IoT. They published messages on different topics, sending us data. We use the message-based or topic-based routing in IoT Core to send these data to different destinations. It could be S3 directly, actually, that we did. We sent all the raw data to S3. We invoked some step functions. We had a SQS queues with a couple of Fargate containers to process the data. We had a lot of these rules. Each rule then has their own topic. You connect the rules to topics, and then you can have filtering on the payload, saying, okay, if this condition is true, then yes, invoke the rule, otherwise not. But each rule needs to be connected to a certain topic to be able to route messages. We had a couple of lessons learned from this architecture that didn't work out very well for us. First of all was actually using IoT Core as our event broker or sending events and data to different services. The problem was that every time we wanted to introduce a new service, we needed to create a new rule. Okay, that's fine. Subscriptions, I like that. However, since it's based on topics, we couldn't do super advanced logic on how to route the messages. because we had to connect the rules to the topic, which means that things grew. So we had very complex rules that did filtering on the payload in a very complex way. And the syntax they're using is SQL-like syntax, which means that the conditions were crazy. And this actually became very, very expensive as well in the end. Our second problem was that we sent data directly from IoT Core into S3. Sounds smart. The problem was that each message coming in ends up as a single object in S3. And the messages coming in are very small, which means that we ended up with a huge amount of small objects in our S3 bucket. Glue, Athena, didn't really like that. There was way too many small objects. And that moving data to other storage classes, like Glacier and so on, became very expensive since there is a minimum limit on those that you have to pay for. And it also made it very hard for us to change data format, because now the devices actually dictates the data format. We found out it was very hard to maintain and extend this solution using IoT Core and the routers as our primary source for events. So we had a theory. Let's go more event-driven. We already beat the event-driven using IoT Core as our event engine. But we said, let's do it even more. So the theory we had was, let's remove IoT Core as our rules router. We, with that, thought that, okay, that will improve our extensibility. And let's introduce Amazon Event Bridge instead as our message router. These also, we said that this will probably lower our cost, because in IoT Core, you pay for each rule that has been invoked and for each action on these rules. You pay 15 cents per rule invocation and 15 cents per action, meaning that if you had one rule, one action, you paid 30 cents per million invocation. Doesn't sound much. Remember the scale. We're talking about millions and millions and millions of devices that might be sending messages every hour, every minute, and so on. The number of messages coming in is huge, which means that the cost was actually going up. And remember, we had several rules with several actions in each of them. So our theory was, let's introduce Event Bridge to lower our cost. What is an event? As we see it, it's a signal to indicate that something has happened or changed. It could be good. New temperature reading, something has changed. A door has opened, something has changed. It's also good, it's immutable, it's observable, it's facts. And it also often comes in JSON format. Amazon Event Bridge, quick overview. Fully managed, 15 plus AWS services as target. API destinations. And one of the primary reasons we looked at is event bridge to event bridge communication, meaning that we could route messages from one bus to another, meaning that our services could be more and more decoupled. It will be easy to build out our event-driven architectures, and it comes with a very low price. We pay for each message ingested into Event Bridge, but we don't have to pay for every single target that's been invoked. There's no extra cost for that. So we changed our architecture to look like something like this instead. We used a single rule, sent all messages to an SQS queue, had a Lambda function being invoked from the SQS queue, sending the message into Event Bridge, and then we did a routing to our Lambda functions, step functions, and so on. That worked really well, but we still hadn't solved the data storage, right? We still sent all of the messages to the S3, still had all of these small objects. So we did one additional change to solve that. We actually dropped the SQS queue and moved to a Kinesis data stream instead. That way, we could connect the fire hose onto the data stream. Now we sent everything into the data stream. We connected the fire hose onto it, and the fire hose dumped our message into S3. Nice buffering, got rid of all the small objects, Glue was happy, we were happy. We kept the Lambda function, so we had a Lambda function that's now being invoked for every message in the data stream, sending data into event bridge. So let's explore that architecture. It was not really that basic, right? It was looking more like this. We have our analytics service that does actually more than just have data in S3. We have an OpenShift, OpenSearch cluster, we have Glue, we have Athena, we have QuickSight, and a lot of other different services to analyze the data. We send all the raw data into this storage, because that's what our data analysts wanted. We actually introduced a new service here, this one, a data transformation service. Since we had several different devices, and all of them wanted to send data in different formats, each of our service then actually needed to understand each service or each device data format. So what we did is we introduced a data transformation service that could do two things. It could convert the data into a more common format, and it could actually augment the data. So it could fetch data from other sources, put that into the event before it's being sent into event bridge. So that service picks up all the data, all the messages coming in, processes and sends it back onto the event bridge. Then our other services on the right side here listens to the transformed data format instead. Looks something like this, very simple step function. If you have been listening to my barbecue talks before, you might recognize this one. We use our SDK integrations mostly in step functions to do our data fetching for DynamoDB and so on. Try and use as little Lambda functions as possible, because why write code if you don't have to, right? So this is kind of the final architecture that we have ended up with. It works pretty well. It serves a lot of different devices. With this, we figured out that we went very serverless, using step functions, lambdas, all the way. The benefits with this architecture is that we can loosely couple all of our services. Every service runs on its own. We can scale and fail independently. So if one of the services, for some reason, stops responding, code error, human error, overload, whatever, it doesn't affect any of the other services. It's very cost efficient. We lower the cost. It's very easy to extend, very easy to build a new service and hook it onto our event bridge. Before, we needed to create this new rule in IoT core. We needed to create this super complex SQL statement and all of that. And it comes with high availability built in, which is nice. I want to highlight one architecture pattern that is key in this architecture, and it's key in my designs all the time. I use it over and over again. And I actually used it the first time in my very first architecture I built in 2016. That time we used API Gateway and SQS. And that pattern, of course, is storage first. Reason for storage first, reliably capture your data before you process it. That way, even if processing fails, you still have the data secured and can reprocess it later. Use managed services all the way. And it's super powerful if your transformation for some reason fails. All right, last section then, takeaway and thoughts. Been a lot here for you to take in, I guess. When using IoT Core, if you run in a large enough scale, it can actually become very expensive, because you pay $1 per million messages being ingested into IoT Core. Once again, you have 2 million devices. Every device sends one message every hour. That's a lot of messages. And you pay $1 for 1 million messages. That can become very expensive. So what to do instead, What we use is reserved topics. Reserved topics is a special topic that starts with $AWS/rules/the rule name. And for us, that had one rule to send all data into EventBridge. This works perfectly. Our devices then can just send to one rule and data is moved on. We can lower the cost significantly using this ingestion. I would say that you should transform, not transport the data using Lambda functions. We're using a Lambda function here to pick. The only thing it does, it takes the messages from Kinesis data stream and sends it onto EventBridge. It doesn't do anything else with the data. It just picks it and moves it. It transports the data. At that time when they built it, we didn't have much other choice. Now, with the introduction of EventBridge pipes, we do have a choice. So that's the next change doing in this architecture, introducing EventBridge pipes. Next, I want to leave you with be kind. You're running a huge scale IoT system. If you are from your services calling a downstream service, third party or your own, be kind. Don't overwhelm the downstream service if it runs into problems. Use architecture patterns like the circuit breaker. Do circuit breaker together with storage first, then you can keep your messages, and if your downstream service is actually down, stop calling it. Be kind. You will overwhelm it in these huge systems. Some thoughts on step functions. We are heavily users of step functions, and there are some things to think about. One thing we early on decided to do was to use the SDK integrations as much as possible. Over 200 SDK integrations, over 9,000 API actions can be called directly from step function without a single line of code. We like that. Why write code if you don't have to? Low code, no code. So that's our key benefit. Don't use Lambda functions in your step functions unless you have to. That's our key takeaway. Express workflows. We extensively use express workflows. Two reasons, basically. On the standard workflow, you have a limit of 2,000 invocations per second. Still, we are talking millions and millions of messages coming in. We can easily hit the 2,000 limits in a search of data. We use express workflows, 100K starts per second. That's enough. And we only pay for the duration and not the state changes. But we learned something the hard way. Express workflows employs at least once model for asynchronous invocation. Meaning you have to consider that. If you run a low-scale system, you will have each invocation being once. But when you run in a huge scale, there will be invocations happening twice for the same message. And we figured that out because we had duplicate of our data in our database and figured out, why do we have this message twice? So we learned that the hard way, you're running it in a huge scale. Make sure you implement idempotency so you can handle this scenario. When it comes to Amazon EventBridge, I normally say create subscriptions. I use a one-to-one mapping, so one rule, one target. Reason for this, if you create one rule, even if we have a support for 5 targets in one rule, what happens if you had 6? Okay, should you create a new rule then? Okay, yes, sure. But what if you remove one target in the previous then? Should you add to then next time? Yeah, the complexity can grow pretty much here. And you create coupling on the filter. So if you need to change that filter for some reason, you will affect all of the targets. And if you don't want that, well, yeah, then you have to start changing all of your rules. So instead, one-to-one mapping, one rule, one target, create the coupling on the event, It's easy to add more targets, and filters can change independently. There is one default event bus per region per AWS account. I say leave it alone. AWS services post messages onto these event bus. Let them post messages on that event bus. Create your own custom buses for your application. Avoid using the default event bus. The reason for that is if you want to create more event buses, then it's easy just to create more and you can connect more services. So it's the same reason we don't use the default VPC, right? Leave it alone. When we talk about event bus and event bus patterns, we can talk about either a single bus centralized pattern or a multi-bus decentralized pattern. There are pros and cons to both of them, of course. In a centralized pattern, you have a central routing, you have a central resource management, and easy to integrate new applications. You have one place, you integrate everything into one place. Disadvantages, becomes a single point of failure, right? And you can actually have leaking business logic. Because if you have a service that needs to communicate internally with events, and you post those events onto the single bus, that business logic can leak into that bus and can leak over to other services. Decentralized and distributed, there's no single point of failure. Each service has its own event bus. It enables autonomy in each service. Each service can then post internal messages how much you want. You don't leak business logic. It's very challenging to design. How do you design with multi-bus structure? Yeah, there's so many ways. And there is way more resources to manage. I would say if you're going to start with a single bus. Start there. Build out your architecture, build it in a single bus, and then grow from that. Don't try to build this huge decentralized event bus structure from the beginning. It will probably be very hard. Start with a single bus and evolve over time instead. Lesson learned over and over again and evolve your architecture. When it comes to data storage, I would say use multiple data storages. We use S3, we use DynamoDB, we use Aurora, everything for different purposes. S3 is our raw data. We have all our time series data in DynamoDB. TimeStream is a really good time series database. And that's very good for analytics queries. We did play around with it, but TimeStream comes with a sub-second query. So we consistently saw query latencies around between 600 and 800 milliseconds. If that query is to fetch data and return to a user dashboard, 800 milliseconds is a very long time. So that was not feasible. It's good for analytics, super good. So that's why we moved back to DynamoDB. So we use DynamoDB as our time streams data for our user-facing dashboards. So, has this architecture been battle tested? I would say so. We run it in several production environments with several different clients I'm helping out. We have thousands and thousands and millions of devices connected to it. We have hundreds of messages per second coming in. And we have a vast amount of data being analyzed over and over again. And most importantly, this architecture actually powers the most amazing system in the entire world. It powers my connected barbecue for great barbecue, of course. With that, I'll say thank you, and I hope you have a good rest of the day.